We're honored to have two gentlemen from Marvell Technologies, one being Gary Kotzer, who's VP of Storage and Chief Technology Officer, leading their storage organization and architecture team. Gary has over 25 years in the computer industry, was previously with Dell EMC prior to joining Marvell in 2020. And Gary's team is responsible for everything from product architecture, their vision for storage and memory products, including HDDs, SSDs, various accelerators, fiber channel, CXL devices, so the full spectrum for his storage operations team. And Gary has quite a diverse background spanning semiconductors from system-level design with expertise in compute, storage, and networking architectures. He's also initiated and been involved in a number of industry standards with many of those organizations that are here today. Gary has also been granted 69 patents for system design, and he additionally has 18 patent applications pending. His degrees are in electrical engineering, bachelor's and master's. Texas A&M, University of Houston, two very good sports teams, I must say. Not sure whether that had anything to do with him picking those schools. And then we have John Haswell, who's Senior Vice President of Firmware for the Storage Products Group at Marvell. And in his role, he's responsible for leading the company's global firmware and software teams to support the Marvell portfolio of products. He joined Marvell in 2018 as VP of Flash Firmware and subsequently became Vice President of the Storage Firmware, and has quite an extensive background in management with a number of memory and data storage companies. He began his career actually with IBM in their hard drive development organization, and continues to serve, continued in various roles within technical and managerial responsibility in IBM's storage division. His work includes research on product development, leading to edge storage technologies for a wide range of architecture. He holds a degree in electrical engineering and has been awarded 15 patents in the area of storage systems and technology. Two impressive individuals. Please welcome them.
Thank you. Thanks, John. Right, well, good morning. Welcome to the first keynote of the day, those who staggered in from any excesses last night. So we're going to be talking here about, cloud-optimized silicon, basically. So first of all, I wanted to talk just a little bit about, and we got this, yes, the evolving cloud. Now, when I wrote this, I didn't realize, actually, I hadn't been thinking about the 35-year anniversary, but I wanted to go back into history, but I decided to go back about 70 years. So what you should see on the screen, I don't know if anyone recognizes it, few do. I mean, I hope that is a picture of an IBM 701, one of the very first sort of mainframe computers in the early 50s. And there's also a very famous quote there, or really a misquote. The quote was they thought there was a market for 5 of these things. Apparently, the full quote is they thought there was a market for 5, but they'd already sold 18 when they made the quote. So obviously, there was demand there, as we well know. Now, going forward a little bit, I always like Steve Jobs' quote from, 25 years ago now, about not needing the hard disk in the computer, given the fast networks. I actually tested this over the weekend. I have an old computer with a hard disk drive in it, and I was testing ping times across the web. My hard disk drive is still beating the web right now. But I'm promised with 5G and the high-speed Ethernet, that will shortly change. And that obviously underpins everything we do in the cloud. Now, we've been computerizing the world collectively for 50, 60, 70 years. And there's been one kind of mystery that the economists look at. Why we've not had a greater impact actually on productivity. If you look at GDP of countries, productivity per worker, it's not actually changed very much from the historical norms. It grows a little bit every year, a few percent. You'd have thought with all this computerization, it would have been on an massive upward trajectory, but it really hasn't been. So I've been wondering why, along with a lot of other people kind of thing. And Larry Ellison's quote, slightly misused here maybe, when he's talking about cloud computing about 14, 15 years ago, we weren't really doing anything different with the cloud than we'd done before, frankly. And if you look at the whole sort of evolution of what we've done with the computers in the last 40, 50 years, particularly in the business realm, we've used them to do what we were doing before, but it hasn't really changed our world. But the question is it going to change our world going forward? There was an interesting article in the New York Times earlier this year, and the quote here is from a professor at Stanford. And basically, his view, and it's one that we hold, Marvell holds, is things are really starting to change now. It may have taken a long time to really work out how to use computers to change the world, but via the cloud, via all the innovation that's going on, the world is really going to be changed by what we do going forward. So in the rest of this talk, I'm going to talk about our view of storage, and then Gary is going to talk about the memory aspects of that. All right, so what is cloud storage? Well, we all know the usual buzzwords, and they're all still true. They're not changing effectively. I mean, the importance of some grows slightly, but it all stays the same. But what we're seeing changing is how people achieve those goals. Historically, if you look through enterprise-level computing, really, the systems were very, very similar. Now, we're seeing massive divergence. We're seeing innovation going on. We're seeing innovations in standards bodies, in, shall we say, pseudo-standards bodies, basically, companies getting together to collaborate to produce a new proposal, which very often ends up in a standards body. And then, particularly in the cloud space, a number of companies who are working on proprietary in-house designs. They see a competitive advantage by redesigning their servers, their storage stack, and their data centers. And, they have the power, they have the finances to do that. So we're seeing, more changes going on here in the industry than, frankly, we've ever really seen before. And if you're going to be a supplier in this industry, it's all about flexibility, configurability, and, being able to meet the needs of the customers. All right. So what does, a silicon supplier, a company like Marvell or Fabless Semiconductor company, need to be successful in this space? So first of all, obviously, access to high technology. We're watching the industry gradually come down the technology curve. As we heard a little bit yesterday, the leading companies are now moving to 5-nanometer silicon. 3-nanometer is not very far behind it. We're seeing a lot of the devices, things I'll talk about in a minute, the devices are getting bigger. There's many more transistors in those devices. You need to be on the latest nodes. Obviously, it's largely about managing the media, so NAND and the other technologies there. And then you have to have all the other composite sort of technologies that go with it in terms of virtualization, security, high-performance compute engines, et cetera. That's sort of a given you need to even enter this market space. Next, it's about flexibility. A lot of companies have a lot of IP blocks, reusable software, reusable firmware. But having that structured in such a way that you can make different solutions for it in a timely manner is key. And that comes down to architecture. Architecture and components, knowing that the way they'll be used is something you probably can't foresee up front effectively, and be able to combine them in different ways is key to success. And then finally, it's about enablement. Typically, what we're seeing for in the hyperscale, the cloud space, is it's really solutions that are needed. Yes, they're based on silicon, but they need to come with the firmware, the device drivers, reference designs for the hardwares, and then it needs to be fully validated, because when it goes into the hyperscaler, they want to qualify it, they want to ramp it quickly. So it has to be the complete package effectively. Each company needs to be able to offer all of these services behind their products. All right. So moving on, one thing that we really believe in the current environment is, there is no one right way to do storage. You need to be agnostic in terms of how storage stacks are put together. There are many different ways to achieve the same end goals, and it's not clear that there is a right way, and certainly for different businesses, they may have their own requirements there. So starting off on the right-hand side here, we see things like the SSD controllers themselves. Some companies are going very much down a sort of commoditized route, keep the SSD as simple as possible. It means you can have multiple suppliers, you have flexibility there. Other companies are putting significant extra function into their SSDs, into the controllers. So, the controller may need to be able to handle virtualization, large quantity of security and encryption. QoS, latency management, is always going to be key. And of course, as we heard in some of the other keynotes, there are more and more interfaces which are being created basically to optimize for different usage conditions. So all of those have to be supported. We're seeing the need, and frankly, it's not a new need, for converters. People have always been converting from one interface standard to another as long as I've been in the industry, frankly. The protocols change, but the need to convert officially between them has not. So, there's a range of converters there, PCIe to Ethernet, for example. SATA and SAS is still, very significant in the hard drive space, which is still tied into storage effectively. So we see a constant demand for this, and often it's interesting combinations, frankly, of converters are being deployed in the hyperscale data centers. And then also, the category which is growing significantly are accelerators. Significantly large pieces of silicon that sit between the host and the SSDs and can offload both the function from the SSD and also, in many cases, from the host, minimizing the CPU workload on the host. And they may be providing virtualization, again, security or encryption, particularly if it's desired to extract that out of the SSD. Also managing QoS in terms of throughput and latency. And now we're also seeing data migration. So features which are typically big box features are now migrating down into these individual silicon devices. So typically we see for success, one needs to have all of these technologies and be able to rapidly and efficiently integrate them into custom pieces of silicon. Powerful and flexible solutions. Our philosophy of design is very much based around programmability. Given the relatively long design cycles for the hardware and yet the very short design cycles that a lot of the customers are wanting to see, you have to have a platform that you can adapt to a particular need. So we typically put in relatively large quantities of compute, embedded CPUs in there, be they ARM, be they RISC-V. The industry's a little bit split on those two right now. They both get the job done. But then also, there's obviously things, relating to the data path that you cannot handle with a standard CPU. So, hardware assist is key, but we are focused on programmable hardware assist, microsequencers, microcontrollers effectively controlling the hardware. So that basically the SoC is a platform on which you can then implement whatever function you need. There is, shall we say, a downside to so much compute power in there, that it literally takes power, it takes energy. So also we're very conscious of needing to make sure that we're using advanced nodes, that we're using the most advanced sort of power control techniques, so we can offer these flexible solutions and still stay within the power budget. Quality of service, I think, is really king here, basically. And we design typically blocks which we can reuse in multiple contexts to ensure that it's possible to give a guaranteed quality of service, because ultimately, from so many of the cloud or the hyperscaler environments, it's quality of service that is being sold. So, at one level, quality of service just relates to the throughput of the devices, and we're seeing increasing the storage stack is having queues of commands coming from more and more applications, virtual machines, etc. So we typically design in flow rate control hardware, programmable, etc. But basically, it's critical in these devices, be it the SSDs or the accelerators, that you can actually provide fairness or whatever algorithm is required in terms of throughput. Next, then, we're looking at QoS in terms of latency, command latencies. And again, we see combinations of hardware and firmware as being critical here. You need the firmware to set the algorithms, etc. But when you're talking about the multi-million IOPS type of throughput of these devices, you have to have a certain amount of hardware assist in there, basically, to track the commands, the command time, and to be able to give that absolutely flat latency curve, which is so desired. It then gets even more complicated, of course, when you get into the multi-tenant environment, but that is where we're all heading. So, we're designing, for example, SSD controllers, and they will support many either physical functions or virtual functions, depending on what the customer wants. And then within the SSD, we actually have a lot of QoS control built in, behind the host interface before one gets down to the actual sort of FTL and NAND management, so that we can programmably, provide that quality of service that the applications need. Beyond that, we can take basically the same QoS logic control, we can embed it in an accelerator. So here, of course, instead of actually having the back end of the SSD inside the device, we simply have more PCIe root complexes with NVMe protocol on them, and you can put this type of device in front of many SSDs. And while obviously you still need to have a high-performance SSD, a lot of the more complicated QoS control can then be abstracted out into the accelerators. All right. I don't think anyone can escape security in this day and age. It's critical, I think, for society trusting, cloud computing, trusting the products that we're selling here. And it's no doubt that it's got a lot more complicated, a lot more complex to provide the sort of security that's required. We're focused on the Confidential Computing Initiative, which is aiming to make sure that data is encrypted at rest, in flight, and in use. And of course, just encrypting it drives a lot of management, key management, et cetera, and the standards that are needed to support all of that and to manage that in itself securely. So it's one thing that we focused on, to have some very robust and certified security blocks, hardware security blocks inside our devices, so that we can support all the latest forms of secure boot, bulk data encryption, and all the management of the protocol. And this is particularly important as the trusted compute enclaves are now being expanded out to include the storage stack, not just implemented on the CPU itself. And then we pair that also with a secure manufacturing supply chain. There is a significant concern that one has to make sure that whatever you design and what you actually qualify is then what is delivered in volume into the data center and is not being tampered with or modified en route. So that's another very important part of the chain as far as we see it. So as I mentioned near the beginning, enablement is also key. You can't take 5 or 6 years to deliver a storage solution anymore. The market won't wait for you, basically. So this is where we believe it's critical to bring all the elements together of delivering a storage solution based on silicon, but with the firmware, with device drivers, et cetera. We're frequently collaborating with our customers, so we're providing them with emulation or modeling platforms so that system software and applications can be developed and tested before the final silicon is available, all to speed things to market. And we have a big focus on what we refer to as A0 to production. Basically, your SoC design process needs to deliver production quality silicon on the first spin of the chip, which is increasingly important as we get down to 5 and 3 nanometer nodes, where not only do the costs go up, but the cycle times in the fab go up as well. And we pair it as well with QA-type functionality, et cetera, so that when a product is shipped to a customer, their qualification cycle is expected to pass first time. And finally, the message is about flexibility. If you're a supplier here, you serve the customers, basically. So we hope we help drive the pace of change here, but we partly do it by having very flexible and configurable solutions, and we're willing to develop fundamentally whatever architecture works for the customer here, using highly programmable components so that we can do this in a timely manner and provide a product which is ready to ramp into production. And with that, I will hand over to Gary, who's going to talk about memory. Oh, okay.
So thanks, John. So now we're going to speed things up. We're going to move from the storage domain to the memory domain. In the memory domain, you have data latencies that are up to 1,000 times lower than they are in storage, which makes memory architectures challenging. Now, we have a new technology called CXL, which is really exciting because it will, we look forward to it changing the data centers of the future. And it does this by providing memory disaggregation, which will be promising for many benefits. So let's talk about some of the commonality between NVMe storage and CXL. And let's talk about how we can leverage them. The first is a cloud environment. We have virtualization, we have multi-tenant, and we have SDS. And as we know, NVMe and CXL both run on top of PCIe. John talked about storage capabilities for the cloud. The same ones are going to be used inside of CXL, such as security, QoS, flexibility, and management. And we have common goals between the two, such as lower power, lower cost, and lower latency. Likewise, we also have needs for higher performance, higher availability, and higher capacity. Let's talk about the industry ecosystem. Customers, the vendors, standards bodies, as well as open initiatives. And then last is the technology enablement, from standalone servers all the way to composable infrastructures that satisfy multiple applications. So let's talk about a few of the memory challenges in the data center. First, we know that memory is tied directly to the processing elements, whether they be CPUs, DPUs, or GPUs. In essence, memory is tethered to these devices, which makes it difficult to share memory resources. In the middle, we have a graph provided by Meta that shows that as core count inside of a processor is increased, we see that the memory channel bandwidth is actually decreasing, which degrades efficiency of your computational complex. And another aspect of the memory being tied directly to the processing elements means that it's very difficult to offload the data computation, again, limiting performance. So today, we know that performance doesn't necessarily scale with capacity. In this example, as we're doubling the capacity by going from 1 DIMM per channel to 2 DIMMs per channel, the problem is that when you have 2 DIMMs per channel, they share that bandwidth, so the performance does not scale, and this caps your performance. In the future, when you want to go to double your capacity, you can now use CXL memory modules, and what you can do now is that you can scale not just your capacity, but also your performance due to the use of the PCIe lanes to provide the optimal bandwidth. Today, servers provision their memory to their most intensive workloads. The problem is that as the workloads vary, stranded memory cannot be shared, which decreases memory utilization. With CXL pooling, we are now able to have multiple hosts talk to a pool of memory. This pool of memory can be redistributed to meet the different varying workloads needs. This improves utilization, reduces overall DRAM needs, and helps to save cost. As an example of this, oops, a little too soon. As an example of this, there was a paper published by Microsoft and Carnegie Mellon that states that data centers can have up to 25% of stranded memory. Using memory disaggregation, we can achieve about a 9 to 10% reduction in overall DRAM. This saves hundreds of millions of dollars for large data centers. Let's talk about the CXL switch. This extends the sharing capabilities, but instead of memory, we're now sharing resources. In this case, it could be an I/O device, it could be an accelerator, it could be a memory expander. This improves scalability as well. In addition, CXL also provides serviceability to minimize downtime for mission-critical applications. As we mentioned before, it is difficult to offload data computation. But now, with a CXL accelerator, you can add an accelerator card that provides near-memory computation. And this can be used for multiple applications. Examples are analytics, AI, ML, could be big data. And this improves the overall efficiency of your most expensive processing elements, such as the CPU and GPU. CXL provides coherent cacheability. This provides accelerations for the different I/O devices that are out there, such as DPUs, or SmartNICs, or SSDs. Earlier, I talked about a few of the memory challenges, and then I claimed that CXL can solve this. So let's go through this. So earlier we said that memory was stranded and memory is tethered. Now with disaggregated memory, we can have full composability. We mentioned earlier about the processors being constrained from adding additional memory channels. Now, using CXL, we can add additional memory and scale performance. Again, talking about offloading of data computation, we can now use memory accelerators in order to achieve that, which gives opportunities to elevate your overall system performance. And we could say now, just to solve these three, that CXL is going to be a game changer for the data centers of the future. So let's talk about a phased approach to full composability. Today, customers use shared nothing servers that are tied together or connected together by Ethernet. In the next phase, we can use these same servers along with external appliances that are tied together by CXL to extend different services. This could be memory pooling, it could be memory expansion, could be accelerators, depending upon what the customer's needs are. And then the final phase, and that will be in the future, is that we can fully disaggregate all of these resources, whether that be compute accelerators, or for memory, or for I/O and storage, all connected together through CXL, a very low latency interface. We would still provide Ethernet for rack-to-rack connectivity. So let's take a step back and look at how we can put this all together. Earlier, we talked about storage. When we combine that with memory, we now have the full solution for data products. And this can be used for both internal and external topologies. So in this example for internal, we have a very simplified view of a two-socket system. On your left, you have the storage domain, which is NVMe with NVMe components. And on the right, you have the memory domain, which is CXL and its components. Now, if you need to extend distances on PCIe, you could always use a retimer. Oh, put a little too fast. But one thing to note here that's important is that everything is being supplied by PCIe. This is a very important aspect for system designers who now have the flexibility to use PCIe for the varying needs. And it also applies to the data center architect who can utilize that same flexibility. So let's turn to external, and we're going to talk about two different options. The first one is NVMe and CXL. On the right, you have CXL that we go external by using a CXL switch, but we can attach the same components, also a very important aspect. But on the memory domain, the storage domain, we're using NVMe over Fabric that goes across Ethernet. Now, disaggregation of memory is relatively, it is not new, but NVMe over Fabric has been more recently introduced for storage aggregation, which is great because it has the high bandwidth and it's very easy to connect multiple platforms across multiple racks. Let's talk about option 2, where we go all in to CXL. If you look at the memory domain, CXL, nothing much has changed, except that we did add a CXL pooling device to the mix. But on the storage domain with NVMe, we've gone a direct connection from the CXL switch down to the NVMe devices, which is achievable by CXL switch. And this is good for use cases of where your solution is inside of one data rack and the customer is looking for extremely low latency. So let's recap. John earlier talked about the evolving cloud and talked about optimizing storage for cloud. This was followed by memory and then also composing solutions. So Marvell is uniquely positioned to help customers with their data center needs. First of all, we have silicon leadership. Marvell has the scale to innovate, and we have a huge commitment to 5 nanometer, which will be expanded to 3 nanometer. We have in-house development for PHY and also IP, and we also have firmware development, courtesy of John, that can provide SDKs, or you can tailor your firmware needs for your product requirements. Next, we have partnerships with many of the memory vendors, both for flash as well as DRAM. And then last, we've made the ecosystem investment to ensure that our solutions work across a multitude of platforms. So whether your needs are storage or memory or both, Marvell is here to help you achieve your goals. Thank you. One thing I'll add is that in the exhibit hall, Marvell does have a booth where we'll be showing demos of the latest storage and CXL innovations. For example, there'll be a memory pooling device, also and SSDs as well. Thank you. Appreciate your time.